Redundant manipulators offer a continuum of solutions for a requested end-effector pose. This is an advantage when operating in confined spaces, but challenges a controller to select a singular goal for path planning. Current methods involve random or user-selected elements to generate the goal configuration. This is effective in free spaces. However, in a confined space, a goal configuration must be generated, which is both collision-free and plannable from the starting configuration. Finding this can take many iterations. Ideally, an assessment shall be made of the start configuration, end-effector goal pose, and environment, so that a goal configuration can be selected which is optimal for the planning task. To achieve this, we propose a method which envelopes all possible configurations across a redundant manipulator's workspace to discretely sample and record a dataset from which a goal configuration may be intelligently selected. We discretize the workspace of the robot into Cartesian end-effector positions. We then discretize the pose of each position into end-effector orientations. For every pose, we generate a sample of manipulator configurations, enveloping all elbow positions and symmetrical configurations. We have used this method to generate a large dataset of over 1 billion configurations spanning the workspace for a KUKA LBR IEWA 14 redundant manipulator. This dataset is stored as a SQL database, which can be queried for manipulator configurations. SQL queries can request any information from the database based on value of or operation performed on the contents. As we have stored the current Cartesian position, we can request configurations based on physical location of the joints. SQL queries also request that the results are sorted by preference, and this is where we can use criteria to select a goal for our planning task. In this work, we search for configurations which are most similar in joint angle to the starting configuration. The database lookup method returns a goal configuration which is not in collision with the walls of the glovebox, is near to the starting configuration in joint space, and where the end effector is near to the requested goal, within the resolution of the database, which in this work is 5 cm. From here, we can use Capellius functionality to drive the end effector from the returned pose to the goal pose. The resulting configuration is used as the goal configuration for the path planner. The iterative method uses existing kinematic solvers to attempt up to 10 times to find a collision-free goal configuration to pass to the path planner. For the scenarios where both the DLM and iterative methods were successful, the DLM achieved reliably higher success rates. The time taken to iterate through the failures also means that the iterative method is more likely to be slower than the DLM. The paths generated also vary greatly with the iterative method. However, the DLM is more likely to produce similar paths in every attempt of the same planning scenario. We have demonstrated the advantages in reliability and repeatability when using the DLM, and further work shall explore a dynamic method of determining the priority of returned configurations.